Now that we've talked a bit about determinants, I want to talk about how row operations that we've studied before can affect them. So let's start out by doing this with a few examples. So to begin with, we have this matrix A here, and we want to do various row operations to it. But first, let's find its determinant. So determinant of A is 1 times minus 1 minus 3 times 2. So that's going to be negative 7. Okay. Oops. Turns out I already have the computation there and forgot about it. Well, that one looks better, so I'll delete this one. Alright, so we have a determinant of minus 7. So let's do this. Let's swap row 1 and row 2. Alright, so that gives us this new matrix B. And let's check the determinant of that and see what happens. Right. So if we take the determinant of this, we have 2 times 3 minus negative 1 times 1, which is 7. And that's the opposite of our original matrix A here. So by flipping these two rows, what we've done is we've changed the sign of the determinant. So keep that in mind. Right? Now, again to this original matrix A, let's take row 2 and multiply it by 4. Right? So this bottom row should become 8 minus 4. Right? So now we have that. Let's do the determinant of this. What do you think happens if we multiply a row by a number? Well, if we do this determinant, we get 1 times negative 4 minus 8 times 3, right? Which, as it turns out, will be minus 28. How does that relate to the original? Actually, let me up here say, remember this was negative determinant A. This one here is 4 times the determinant of A. So if we take a row and we multiply it by a number, we end up multiplying the determinant by that same number. So one thing I'm going to leave you to think about is, what if we multiply every row in a matrix by a number, right? If we take like 4 times the matrix A. Think about what that would give us. Lastly, let's say we take a combination of rows. So 2 times row 1, add that to row 2. Right? So again, we're going to do that to the original matrix here. 2 times row 1, add that to row 2. And we get this matrix D. What do you think is going to happen here? This is probably the most mysterious of all of them as to what it might do. Right? This constant multiple one probably makes a little bit of sense. Here, we're flipping two things. So when you flip things around, getting a negative isn't that surprising. However, what's going to happen here? Well, let's find out. Determinant of D is 1 times 5 minus 3 times 4. So that's 5 minus 12, which is negative 7. And look at that. That's exactly the same as the determinant of A. So what does this all mean for us at the end of the day? So here, we only did this on example of a 2 by 2 matrix. So, we haven't proved in any way what I'm about to write down. There's still a lot to show. But it gives us an idea of how row operations are going to affect determinants. So let's write down this theorem. Right, so what we're going to do is let A and B be square matrices. Then 1, when B is obtained from A by interchanging 2 rows, the determinant of B is going to be negative the determinant of A. Okay. Now here, it doesn't matter what the size of the matrices are. These are just generic n by n matrices. But if we take a matrix and we flip 2 rows, that new matrix, the determinant of that is the negative of the original. Okay. 2. When B is obtained from A by adding a multiple of 1 row, or sorry, of a row of A to another row of A, when we do that, the determinant isn't affected at all. Oops. And to write determinant of B is determinant of A. All right. So that's a formalization of the other thing. And last thing, when B is obtained from A by multiplying a row of A by a non-zero constant on C. Right? When that's the case, the determinant of B is C times the determinant of A. So this theorem here can be very useful for computing determinants of matrices. Because what it's saying is that if we allow, or if we start with a matrix that looks big and complicated, but we perform row operations on it first to turn it into a simpler matrix, we now are able to compute the determinant of a much easier matrix. So if we do that, though, we have to keep track of the changes we make. All right. So with that, I will end here for this video, and then we'll do an example of using this theorem in the next video.